I would now present the next chapter that is going to be presented by Bjørn Isaksen about risk and reliability. Please, Bjørn, you can proceed.
Thank you. Risk and reliability, and I will try to cover the following headlines. Specific hazards for SFTB, stability of floating structures, ultimate limit state design, target reliability, and verification methods. Specific hazards for SFTB and some site-specific scenarios may be ship impact, submarine impact, sinking ship, unintended drop anchor, drag anchor, landslide, underwater landslide, tsunami, seismic activity. And I have separated this in specific scenarios, and more in general, we have consequences of leakage, fire and explosion, and consecutive damage or component failure that leads to system failure. The hazard listed here call for robustness and redundancy in design. The ISO 2394 general principles on reliability for structures given in 2015 introduces the criteria and gives guidance on how to perform a risk analysis. We are here talking about risks during construction, installation, and operation. And it is necessary to consider construction and installation, not only operation of the SFTB. Stability of floating structures. Net buoyancy. The SFTB is partly a weight buoyancy stabilized structure, so that a robust regime for the net buoyancy will have to be established. The design should be based on upper and lower characteristic values for self-weight and buoyancy, including geometric and density tolerances. Weight and ballast reserves for the tube bridge should be specified and coupled with weight control program. The design assumptions on permanent self-weight can be checked by the possibility of weight tuning while afloat, for instance in dock. Parts of the variable self-weight to consider may be time dependent, such as marine growth and water absorption of concrete and solid ballast. Mooring system. Design criteria for tether slack control during dynamic response of the SFTB will have to be defined in order to warrant global stability. Normally, the requirement on net buoyancy is that tension shall be maintained in all tethers for the most onerous combination of unfactored characteristic loads. Whereas tether slack can be accepted in the ultimate limit state without causing structural failure or tether unlocking. The risk of unexpected loss of a tether or pontoon should be assessed as part of the risk analysis. Floating stability. For a free surface stabilized SFTB, the minimum freeboard should be greater than 0 for the most onerous combination of characteristic wave and tide conditions. ultimate limit state design. First, let me comment on some important principles in Eurocode. Design situations. Design situations are categorized as persistent, transient, accidental, or seismic. These categorizations draw together families of circumstances or conditions that the structure might experience during its life. Persistent design situations refer to conditions of normal use, such as for a bridge, they will include the passage of heavy vehicles, since the ability to carry heavy vehicles is a key functional requirement. Transient design situations refer to circumstances when the structure itself, in some temporary configurations, such as during execution or maintenance. Accidental design situations refer to exceptional circumstances when a structure is experiencing an extreme accidental event. Reverse and irreversible serviceability limit states. The Eurocodes differentiate between reversible and irreversible serviceability limit states. Irreversible serviceability limit states are of greater concern than reversible serviceability limit states. The acceptable probability of an irreversible serviceability limit state being exceeded is lower than that for a reversible serviceability limit state. A more onerous combination of actions is used for irreversible serviceability limit states than for reversible. So, a little bit of representative values of variable action. There are 4 different representative values of a variable action. The characteristic value is a statistically extreme value. It is the main representative value and the value generally defined in Eurocode 1991. The other representative values are called the combination value, frequent value, and quasi-permanent value. They are determined by multiplying the characteristic value by C index 1, 0, 1, and 2, respectively. The combination, frequent, and quasi-permanent values are less statistically extreme than the characteristic values, so C0, 1, and 2 are always less than 1. Ultimate limit states. The Eurocode explicitly established 6 different ultimate limit states. 2 of these are, and I now use the acronyms, UPL and HID, are specific to 1997, that's GEO. 2 are concerned with resistances, STR, when verifying structural resistance, and GEO when verifying the resistance of the ground. FIT is concerned with fatigue. EQY is principally concerned with ultimate limit states involving a loss of overall equilibrium. However, it is an important relationship with the single source principle. Different partial factors on actions and geotechnical material properties are used for different ultimate limit states. Single source principle. Application of the single source principle allows a single partial factor to be applied to the whole of an action arising from a single source. The value of the partial factor used depends on whether the resulting action effect is favorable or unfavorable. EN 1990, basis for design, allows the single source principle to be used for STR and GEO verifications. EQY addresses cases when minor variations in the magnitude or spatial distribution of a permanent action from a single source are significant. Combinations of actions. EN 1990, that is basis of design, establishes 6 different combinations of actions relevant to bridge design. Different combinations of actions are used for verifying different limit states. They have different statistical likelihoods of occurring. The quasi-permanent combination is also used when analyzing long-term effects. The differences between the combinations of actions concern whether partial factors are applied, which representative values of variable actions are used, and whether there is an accidental or seismic action included. The different combinations of actions are used in conjunction with Eurocode material parts. The Eurocode part generally states explicitly which combination is to be used in each SLS verification. Ultimate limit states. Limit state design is widely accepted and is also recommended for design of SFTB. 1. Exceedance of static equilibrium, including loss of buoyancy and slack in tethers. That's EQY. 2. Exceedance of strength or strain limits. That's STR. 3. Exceedance of fatigue strengths. That's FIT. And 4. Exceedance of geotechnical equilibrium and deformation limits. That's GEO. One example. Leakage water shall be treated different compared to rock tunnels or immersed tunnels. Leakage may be relevant in the ultimate limit state of static equilibrium. So, target reliability. To meet the target reliability, SFTBs might need higher requirements and higher safety margins compared to other structures, for instance, bridges, since SFTBs will be prone to more and different risks. And second, SFTB is a new structural concept. Here I have given a figure in the document. It's table 12.2, I guess, showing some figures, the probability of failure and the beta values. The probability of failure is, of course, a very, very small value indicating probability, and beta is an equal parameter explain or giving the same information. I can try to give you a simple mathematical explanation of beta. Considering the limit state function, or for instance, strength minus load, it should always be bigger than 0. And the statistical variables involved in that expression. Then transformate or make a mathematical transformation of the variables to the normalized space. And And if you see this in 2 or 3 dimensions, this can be shown graphically. And beta is then seen as the distance from origo to the design point. I think the table shown here, it shows small values for the probability of failure, but even so, it's not unusual to see 10 to -6 regarding bridges. There are indications showing that the target reliability related to offshore structures is hard to achieve. However, this is not equal to say that offshore structures are unsafe. It's more like saying that target reliability is a theoretical goal. So, this is my last slide. It's on verification methods. I do not dare to dig deeper into this subject, which is very complex and complicated. And I will only give reference to further reading in 12.4 and 12.5 given in the bulletin. Thank you.
Thank you very much, Bjørn.